Let's continue our discussion of residuals and outliers and regression diagnostics by talking about outliers and leverage. We'll wrap it up with this little segment here. Just a couple of definitions. Outliers refer to very, very large or very, very small y values. Again, y values far away from the others or far away from the average, if you will. On the other hand, leverage refers to very, very large or very, very small x values, or values in independent variables. Okay, so we have outliers, we have leverage. Sometimes it gets grouped on and we just call them influential observations, and sometimes that's a nicer term to use because it captures both situations and gets the point across. So why do we care about these so-called influential observations? Okay, so you got a large X, you got a really small Y. So what? Why do we care? Well, the problem is if you have smaller data sets especially, is that this particular single data point can have a disproportionate impact on estimating the slopes, estimating the intercept, and estimating predicted values for the Y. Okay? So we're okay if it has some impact, because every observation has some impact. But what we don't want is where one observation or two observations have a really, really strong, overwhelming impact on our results, because then we don't really have a large-ish sample. We have really one or two observations that are driving everything. So is that really indicative of the relationship we're trying to model? Don't really know, because these very small number of observations, or these influential observations, are having so much impact on our results. So you can kind of see from the graph here, we have an outlier for a Y, and in this case it's just a very, very small Y, very much different than all the others. You know, one of these things is not like the other. One of these things just doesn't belong. Okay, and so here's what we have, right? So now, is this a bad point? We don't know. It bears further investigation. Was there a mistake? Is this legitimate? It requires follow-up. Okay, and so you can kind of see here's the line drawn as a result of this, with this particular point in the data set. And now we draw the line without it in there, right? And it does change a little bit, right? Line bounces up because this influential observation, or this outlier, is pulling that line down towards it. Right? So making the relationship different. Oops. Okay. Which one's the true observation? Well, we're hard to certain to say, but likely the second one is likely. But again, that existence of that outlier means, hey, further investigation on this point is necessary. Same kind of idea with leverage values. So we have price versus kilometers and price versus age. And you can kind of see encircled in red the respective very, very, in this case, very, very large X variables, right? And when you look across that X-axis, we have this car here, price versus kilometers. And price are kilometers that seems to be around like 900,000 kilometers. Now, is that realistic? Hard to say, right? Same thing here, where we have a 10-year-old car, but it has a high value, a high price relative to what other similarly priced vehicles are at. I mean, typically in this data set here, we're looking at the $30,000-ish, $25,000, $30,000 cars typically are 0 to 2 years old. Here we have a 10-year-old car that's at $30,000. Now, perhaps it's a very expensive car, and it may not be a mistake, but it could be that we're throwing in a Corvette in amongst a bunch of Corollas or something like that. And is that really what we're trying to model? Or perhaps that particular result doesn't belong, not because of a mistake, but because it isn't typical of the other cars that we're modeling. Okay, so there can be a lot of things going on, and it requires, us thinking, right? The numbers, the measures that we'll talk about will, throw out and say, hey, this is a potential observation to look at. but it still comes down to our judgment as to whether that observation is a problem or not. So we have the relationship with the price versus kilometers with that one really, really high leveraged value. And you can kind of see when we look at that line does not look like it's typical of the flow of the data, right? I mean, what do we do about this whole middle part here? Is there really a relationship there when there's no data points? Ugh. I wouldn't be comfortable making a whole bunch of inferences on this because this is a pretty ugly line, right? If it's so-called corrected, perhaps it was a mistake, or perhaps it was an observation that didn't belong with the rest of this data set. You know, it was measuring something else. Right? And when we look at the second line, we can kind of see, well, that second line is a little bit more indicative of the relationship that the data is indicating. Okay, and when we stretch it out even further, right, and then put it to scale, it looks even more reassuring that, you know, perhaps that observation, that leveraged value maybe didn't belong for whatever reason. Again, mistaken data entry, or perhaps it's just an observation that is not doesn't have the similar attributes as the others, and therefore isn't going to help show the relationship that we're hoping to illustrate here. I.e., this price versus kilometers relationship may hold for certain types of cars and not so much for other types of cars. And so we have a bunch of measures for indicating influential points. Okay, and you can typically find these on the formula sheet, or you can derive your own formula sheet that has these on it. Okay, so we have this influential point called the leverage. Now, I'm not to say in any way, oh my gosh, we got to do this calculation where we're finding the standard deviation of the ith residual, we have a standard error of the estimate, and then we have this complicated H formula with all this other high intensity, high labor kind of calculations involved in it. No. Okay. From a practical matter, we depend on the technology, computer programs, the stats packages to give us these values. Okay, so we're not calculating these values ourselves directly, but how do we determine whether that value is a problem or not, or of concern or not? Well, that is something we can calculate. So the H leverage, the leverage stat, is derived from, you know, a stats package, R or whatever stats package you happen to use. It won't be Excel. Excel doesn't do this unless you want to write your own macro. However, we do have some values here. And when we look at the values, we say, okay, PP is the number of predictors, number of independent variables. Well, that's easy to figure out. N is the sample size, as it's always been. Okay, so we do this calculation, we come up with a cutoff value. So if the computer package is spitting out a leverage value higher than what we've determined this cutoff value to be, then that's potentially problematic. Okay, I'm not ready to say it's a problem yet, but it's a one sort of piece of the problem puzzle, if you will. Cook's D, again, nasty looking calculation involved there with that H statistic that looked really scary before, and we toss in some MSE, and we toss in some I minus Y hats, and this is just really a dog's breakfast here, right? And it's just a simple situation. Right? Again, we let the computer do the grunt calculations, okay? Those grunt calculations, we let the stats package do. What we look at those Cook's D statistics, and if you get a Cook's D that's greater than or equal to 1, that's an observation whose influence is large. Okay, cool. That's pretty easy to do, right? It just requires you to kind of go through the list. Now, if you want to get really cool about it, you can get the results, and in Excel do conditional formatting, highlight in red the ones that are greater than or equal to 1. Whatever rocks your boat. But it's easy to work with, right? These influential observations, they're just checklists, right? Leverage is large when we get a value out of the stats package of 2 times p plus 1 divided by n. Okay, so I look for numbers bigger than that particular value. Cook's D, I look for ones. Okay, I look for those Cook's D, any of them greater than or equal to 1. Right? Pretty straightforward stuff. Keeping on with our theme of pretty straightforward stuff, we look at the T-residuals. Okay, and again, calculated using some sort of stats package. Is not going to be something that we're going to be easily being able to do, punch out with a couple of, punch a couple of numbers in your calculator and something is going to come out. It won't be like that. It involves a little bit of technology. However, in evaluating it, which is what we're all about, is easy. We look for the absolute value of those T-residuals, or their cousin, the studentized residuals. And if the absolute value is greater than or equal to 2, possibly a problem. Now, this is a little bit of an arbitrary cutoff. Some folks, some statisticians prefer it to be greater than or equal to 3. Okay, our main use textbook uses 2. Not going to say 3 is wrong, right? But at least 2. Okay, so if you get that T residual, absolute value of it greater than 2, potentially problematic. Now, that means the greater than 2 just means it's far away from the others, right? So that's why we do the absolute value, because minus 2 does not make us happy, and plus 2 make us happy. Now, they're both kind of concerning. Okay, so continuing on with our checklist, we go into the values I find the most interesting and the most useful is first of all the DF fits, which just looks at the y-hats, and the DF betas, which looks at the slopes, because these things tell us a little bit more information. We start off with, again, the calculation for the DF fit statistic itself is done by the computer package. Okay. However, we can determine whether that computer package generated number is of concern or not, or if its influence is large or not, by looking at its cutoff point. And for this one, the cutoff point is 2 times the square root of p plus 1. Again, p is still the number of independent variables, and divided by that all by the square root of n, and n is still the sample size, so it's still plug and play. Right? We calculate the cutoff value. We look at our results from our computer package. We see if that cutoff value for the DF fits is bigger than this number. And again, just like we did with the T residuals and the studentized residuals, we look at those DF fits, the absolute value of them. Okay. One little caveat, sort of a little bit of a disclaimer that goes with this DF fits statistic, is it may miss an influential point if there are 2 points closer together. It may pick up on one and not pick up on the other. Not every time, but sometimes it's been known to happen. So just a little bit of a concern there. And now the DF betas. Okay, so we remember from when we're doing regression in general, right? We have beta 0, which is the intercept, beta 1, which is the first slope, beta 2, which is the second slope, beta 3, which is the third slope, and so on. Well, we're going to have a DF beta statistic for each one of those betas. So there'll be a DF beta 0, a DF beta 1, a DF beta 2, a DF beta 3, again, for every one of the intercept and then every one of the slopes, or the intercept and every one of the slopes. Okay, cool. Nevertheless, regardless of whether it's a DF beta for the intercept or any of the slopes, we have a cutoff value again. The technology will calculate the DF beta statistic itself for that particular observation. We'll look at the absolute value of that DF beta statistic that was calculated for us by the stats package, and if that number is greater than or equal to 2 divided by the square root of n, then, hey, you may have a potential influential observation. Now, you'll notice we have a lot of measures here, and they don't always agree. So whenever we're going to say, hey, this may be a potentially influential observation, we want to make sure that at least two of these measures suggest that you have an influential observation. Okay, so we want to make sure that at least 2 of them. And then we'll say, okay, that's an influential observation because of this, and then we explain it's because it had a leverage value greater than the leverage cutoff of this, or we had a df beta value, df beta 0 value greater than the cutoff for df beta of this, and so on. Okay. And lastly, and probably most importantly, is those df beta statistics tell us a little extra story. So the df beta 0, which relates to the intercept, if it's positive, then that means that the intercept, our estimated intercept, is larger because of the outlier, right? Positive number, larger. And if we have a df beta 0 that's negative, that's telling us that this particular influential observation is making our estimate for the intercept smaller than it otherwise would be. So that's a very important result. Now another very important result is looking at the df betas for the slopes, whether it's df beta 1, df beta 2, df beta 3, whatever the case may be. Again, if you have a positive number for that df beta 1, 2, or whatever it is, that's telling us that the slope is being made steeper because of the influential observation. Okay, the slope is being a positive df beta 1 or 2 or 3 or 4, right, indicates that that's the slope, that particular slope is being made larger or steeper because of that or due to that influential observation. Conversely, if you have a negative df beta 1 or higher, then that indicates that that particular influential observation is making that particular slope shallower or smaller. Okay, so very, very, very important result there. Okay, so let's look at some sample results. So the results come out and we get a residual amount, which is just the value of the error, a studentized T-residuals, T-residual, leverage, Cook's D, DF fits, DF beta 0, DF beta 1. This is just done on a simple linear regression, so it stops at the DF beta 1, but it could easily be a DF beta 2 and further. Okay, it's just harder to do because it's limited screen time, but the idea stays the same. So we had C-circle. We look at observation 1, we look at observation 3, sorry, and we see for observation 1 we have studentized residual of 2.3, again higher than our cutoff of 2. We have a T-residual of 3.8, again it's higher than our T-residual of 2 cutoff. So okay, so there's two measures suggesting that observation 1 is potentially an influential observation. Observation 3, well, mixed results there, right? We get a minus 1.82, absolute value of that is 1.82. That is below our cutoff value of 2. So the studentized residual is telling us, maybe it's not so influential. But the T-residual is telling us the opposite story. And this can kind of be sort of a theme throughout this process. It's not a absolute, cutoff, if you red line kind of, crossed the red line and all sorts of bad things happen. It's a process. It's a shifting of grays, if you will. Okay. So observation 1, we can kind of see that that's going to be an influential observation just based on those two statistics. Observation 3, we're not so sure. Right? Some of the easy ones, the easy kind of measures we have is Cook's D. Right? Is a Cook's D greater than 1? I look down there. Whoa! Observation 1, big Cook's D, 1.98. That is like huge. Cook's D is a very conservative measure. It's not very often that you get to 1, and so when you get way past 1, that means that that observation is really, really influential. So we see a Cook's D of 1.98. Okay, further solidifying what the studentized and the T-residuals are showing us. But observation 3, 0.66, also very high, but not quite 1. So we're not sure in that particular regard. So in that case, we really don't know. Right? Now for leverage and for the DF fits and the DF beta 0 for the intercept and DF beta 1, now we depend a little bit on calculating the cutoff values. Okay, so those ones depend a little bit more on finding sort of cutoff values for those particular measures, and then using that in order to identify whether an observation is influential or not. So let's do that right now. Let's look at leverage now. So let's look at that leverage statistic. Now remember, it's high if HI is greater than 2p plus 1 over n. Okay, so here we only have 1p, so the leverage cutoff is 1 plus 1 divided by n, and we'll assume that's 10 observations. Okay, and that means 0.4 in this particular situation. Okay. So if we have a leverage statistic higher than 0.4, potential problem area. Okay. So let's look and see our leverage, and we see again observation 1. Yeah, ooh, knew that one was trouble, right? And again, leverage 0.43, higher than the 4. So again, another statistic that indicates that observation 1 is an influential observation. None of the other observations has a leverage of 0.4 or higher. Okay, so the other statistics, so far we're not seeing anybody that's really jumping out at us. We look at our observation 3, it's got one that says yes, so it's sort of at the cusp, right? And so we're going to look at it a little more closely, but the other ones look like not only are they not past the cutoff, they're well below the cutoff values. Okay, so let's look at another leverage cutoff value, and that's for DF fits. DF fits. Okay, and so we kind of look at our DF fits test statistic and look and see, hey, is this one high or not high? And so DF fits, again, the absolute value of the DF fits is high if this one is greater than, it's greater than equal, technically, 2 square root of p plus 1 all over the square root of n. So that cutoff value is 2 square root of 1 plus 1 divided by square root of 10. Right? And then we can look and we'll calculate that number. And that number is 0.89 or so. Okay, so now we can look at our selection of DF fits and looking for a number whose absolute value is higher than 0.9. And aha, so again, observation 1, very high DF fits value, 3.19. So again, really solidifies the story that observation 1 is an influential observation. However, now observation 3, now we've got that second statistic that's indicating that observation 3 is indeed influential. And remember, we're taking the absolute value of that minus 1.4, and we get 1.4. That is definitely greater than 0.89. Our second statistic is in place, indicating that observation 3 is indeed an influential observation. We see the positive nature of the DF fits, indicating that observation 1 is pulling the line up, and a negative aspect of our negative value for observation 3, indicating that observation 3 is pulling the line down. Okay? So it's an extra piece of useful information there. Okay. Now last, let's look at the DF betas. Okay, so DF beta, so value is high or large if, again, greater than, equal to 2 over the square root of n. Okay, and we can then find that one as well and determine whether that DF beta 1 is DF beta 0 or DF beta 1 is large. And when we chug that one through, we get that number equals 0.63. Okay, so we're looking for the DF beta either 0 or DF beta 1 where their absolute value is greater than 0.63. And observation 1, unsurprisingly, it shows this. And in DF beta 1 for observation 3, that number is higher than 0.63. So that's indicating that's yet one more. It's our sort of our third test statistic that shows that observation 3 is influential. Okay. We can also look and see, do some discussion on how these particular observations are impacting the intercept. Okay, so the intercept's being made a little bit smaller because of the DF observation 1, a negative number there, and DF beta of 2 positive number is indicating that observation 1 is making that slope a little steeper. Okay, so it's kind of pivoting a little bit. It's pulling the intercept down, making the line a little steeper, right? And you can kind of see how that goes. And then the DF fits is kind of trying to pull it up a little bit. But we see a strong influence on making that slope steeper. Conversely, with observation 3, the observation 3 is trying to make that slope less steep. So kind of, I wouldn't say canceling out, but sort of counterbalancing a little bit the impact of observation 1. Okay. So observation 1 happens to be, this is for beer and marketing. Observation 1 relates to Budweiser, and they had higher than predicted shipments, so way to go. They did much better than expected. Miller Lite had lower than predicted shipments, and so they're kind of an outlier on the negative side. Now, how do we know they're higher and lower? Look at those student-eyes residuals, because they're positive, right? Indicates that it was the you go look at observed minus predicted. We get a positive number. That means the observed was much larger than what we thought it would be, or what the predicted was. So positive number, higher than expected. And then we get a negative one. A negative value means, okay, what we observed was smaller than what we predicted. Right? Y hat is what we predict, right? And then so we get a negative number, and it means that in this case shipments were lower than expected. Okay. And then we have the graph, and you could probably guess which one is observation 1. They're not sequential left to right kind of observations, but you could probably guess it. Hey, higher than expected by a lot. You'd be looking for it well above the line, right? Lower than expected by a lot. You'd be looking for something quite a bit different from the line. You know? Observation 1. Up high, observation 3 down low, right? And you can kind of see the impacts that these are having, like a teeter-totter, right? So you can see where this observation 1 would be pulling that line up towards it, and observation 3 would be pulling that line, or pulling that, making that little slope a little gentler, and sort of making that slope shallower and pulling the line towards it. Da-da-da. And so there they lie. Okay, so very much a kind of paint by the numbers kind of calculation. Okay, the rest of the slides will go through it and highlight it in a nice reds where necessary, and so on. Okay. All right. So I encourage you to try the other couple of examples that are on this slide set. Okay, so we have our friend predicting weekly gross revenue using just television advertising, so one Y, one X variable. We can extend it to being multiple X's. It just, the limitations of putting tables on slides just mean one X variable, but there's nothing magical about it. Oh, can you only have one X? No, you can have as many independent variables that you normally would have. Okay? And so we see coming out on our data set a set of influential observation calculations. Okay. Our goal is to determine what the cutoffs are for leverage and the DF fits, the DF betas, okay, and then look at those particular test statistics themselves, or those particular statistics themselves, those particular statistics themselves, and see if they're higher than our calculated cutoff. Okay. Same story with the next data set, just extra practice. It's just really, you calculate those cutoffs, and then you just roll through and see if these particular calculated values are higher than those cutoffs or not. Okay? And importantly, keep in mind the impact that the particular observation has on either the intercept via the df beta 0 calculation or a slope via a df beta 1 or higher calculation. Okay? That is very, very important as well. Can't emphasize that enough. That is very, very important result of the df beta calculations. And that is it for this particular segment.